is the second lecture of today for the thermal experiments.
Thank you. Okay, let's continue on yesterday. So we the main thing out from yesterday's lecture was this formula. This is the drawing density or marginal sum F L tau. So cumulant and its cumulant is a sum of these quantities, over all the molecules M. So let me do a little bit of Build notations because really we're interested in L1 normal EH. So everything here is measured in L1. So for example, we're measuring approximating this joint density as particle density in L1. And then this is a solution of the Boltzmann, so and this guy you just need to measure in L1, and you want to show basically if H is empty, this is one, there is nothing, and you have the tensor product. Now, if H is not empty, you want to show that the terms vanish in L1. So basically, you want to show that the L1 normal EH kind of vanishes in the limit. And so really, we're interested in L1 norm of these EH, and we're interested in L1 norm of these expressions. So since we still have not yet introduced these expressions, so let me just build the notation a little bit and call the L1 norm as IM. This is and we'll see this with this definition. This is a more kind of slightly more convenient way to write it. Okay, so this is this, and of course from this second thing we immediately get this L1 norm of EH is less than the number of molecules M times the 2 in M of these IMs. Okay, so here we are maybe restricting M to subclasses, like with a certain size and certain number of cycles, we'll see. But essentially, it's a number of these. Well, we're solving this counting problem and the problem of estimating these individual IM. So let me explain what M is and what IM is, just to start today's lecture. So first of all, M, we already see M is a molecule, and which is we already discussed last time, but it has a special structure. So remember, we're having these different layers. So M formed by this, let's say ML minus 1 up to M1. So this is a layered molecule. And then at each layer, there is a certain set of root particles. Think of each particle is represented by a trajectory, like we draw yesterday concerning different colors represent different particles. Okay, and we consider those set of particles that cross a certain layer. So let's say this way. So let's say you have this this maybe L tau. There is this L minus 1 tau. So L is a large number, which is constant, and then there is, let's say, L minus 2 tau. That's all. So let's say in the beginning we have this set of root particles, the particles in H, okay, because this EH is a cumulant. We're interested in the study of these particles, so we draw them as let's see the blue lines, and for this, okay, and we look at the collisions in this layer. So this would be the ML. This would be the part, ML, this will be the ML minus 1, and so on. Okay, and look at all the collisions of these. Here, there's 3 particles. There are collisions here, and there are, for example, collisions that goes like this. Okay, and there are more. There are collisions that go like this. Okay, so if you look at these collisions, now these 3 blue particles, now they are embedded into these 1, 2, 3, 4, 5 particles. Okay, so because there are 3 particles and they in this layer ML, they collide with themselves and they collide with other particles, and your total have 5 particles. Okay, and you look at these 5 particles. So let's say some of these particles they belong to the factorized parts in the time L-1, and we don't care about them. And some particles they belong to the equivalent part in this time L-1, and we keep expanding them. We draw them as red. Okay, so this, let's say 2 of them are red, and these things are the particles that cross these into this layer L-1. Okay, so this is the root. This is the root. We call the set Rn of L. So R is for root, and this is for the blue ones, and these blue ones are R of M L-1. Okay, so these are the particles where they occur in accumulants. You need to further expand them, so their trajectories you allow them to cross into the previous layers. Okay, and then these red ones, they collide. Okay, they collide like this, and then maybe they have a further collision like this. So have there's a 1, 2, 3, 4. These two red particles, go down to this layer L-1. They collide again with other things. You get total of 4 particles, and then there is this among these 4 particles, there are these, for example, this one that gets into the further layer. Okay, and then okay, so and this one they don't, and then you look at this L-3 top and so on. This will be the layer ML-3. And all the way get back to time 0. At time 0, there is no more accumulant, so just everything just stops. Okay, so this is the picture. And last time I already mentioned that there is one more property. Let me just recall that this R of ML set of particles crossing into layer L from higher layers, like the blues, they cross into layer L. This guy is layer L from higher layers, and the red again cross into layer L-1 from the higher layers. This is red, and this is the green, those crossing into layer L-2. Okay, and then in the end of last lecture, also mentioned this important property of the molecule, that is each layer. So each R, M, L, let's say each of the blue ones, they either connects to another blue one in this layer L. Okay. For example, this blue one connects to this blue one within this layer L. They're connecting, going down here, connects. Or to R of M L-1 in M. ML-1 is a red one. So each blue one, they either connect to itself, or this guy is not connected to other things, but they are connected to the red in this segment. Okay, and the same thing, the red ones, they either they're not connected to this layer, but they're connected to the green one, and so on. Okay, so this is a key property, because we said last time, if this condition is not satisfied, then you'll be able to extract a factorized term, and the term will not belong to the accumulant H. Okay, so this property of the molecule is very important. So basically, it's from here we can derive this next statement, which we actually use in the proof as from this statement. This statement of corollary that each particle in R of ML is connected to another particle in R of ML, but not necessarily in this layer ML, in layers ML union ML minus 1 union M1, basically in the layers L and below. Okay, let's look at this picture. So let's complete the picture because see there is this green, and then you have this and you have this, and maybe you're having with others and so on. So okay. Something like that. Okay. So then you see things that each particle line. So let's say look at this blue one. It is okay. So if it's connected to another blue one in this layer, like this one, then you are good. Of course, you're just directly connected to another blue one in this layer. This is alpha ML, and this is ML minus L minus 2. So in this case, L will be 3. Okay. So now let's say this blue one is not connected to other blue ones via this layer, but then it's connected to the red one. Connected to the red one, which means connected to the red one means you can go further down. And then for this red one, again, whether it's connected to another red one in this next layer, or it's further connected to green one downstairs. And you can keep tracking in the very end level, in the very last level, the green one has to be connected to another green one because there is no more equivalent times 0. Because this is 0, so L equals 3. So this is 0. Imagine this is 0. This is 1. Because at time 0, there is no more equivalent, so this green one has to be connected to this green one in this bottom layer, which is the first layer M1. Okay, just saying you look at this blue one, you go down. Either you're direct connected, you are good. Either you're direct connected, you are good, or you can go down here. Down here, you go from blue to red. And for the red, either you connect to another red, and then you can again connect it to another blue. And then otherwise you are connected to green. And down to green, you have to be connected to another green. So it has to connect to another green, and the green will connect to red, and the red will be connected to another blue. And finally, by going through these edges, you can connect this blue to another blue, which tells you this. Okay. So this is a very important property of the graph, which comes from the fact that each time we are only kind of expanding the cumulants, but never expanding those factorized part, which they are already solution both. Because if you try to expand the Boltzmann, you're trying to expand the Duhamel evolution, Duhamel expansion of Boltzmann, which will not necessarily converge. But okay. So this is the M. Okay. And well, there are a few other simplification we make, but we'll get to that when we discuss the algorithm. So is there any questions? Yes.
Okay, what are the blues?
Blues are so remember we are calculating this EH. EH is a cumulant involving a number of particles. So these blues are those represent the trajectories of those particles in H. Okay, we start from a number of particles.
Okay.
Okay.
And also because the roots of the ML, they are disjoint to L.
They are what do you mean?
This says roots of ML.
Yes.
Is it disjoint from roots of MJ?
Not necessarily. There can be common element. Some of the blue can be coincide with some of the red, but it doesn't matter as long as you have that good definition for each blue and each red. Okay, think of it this way. You have particles, number 1, 2, 3. These are number 1, 2, 3. Okay, in this layer, and then you have collisions, and collision brings you 2 more particles, 4 and 5. And then you have total particles 1, 2, 3, 4, 5, and then you choose an arbitrary set of those particles. Those particles are the red, and choose the 2 particles. They can contain something in blue, 1, 2, 3. They can be 4 or 5, right? Because think of this way. So you have this 1, 2, 3, which are the root particles you are looking at in the EH, because every formula is about EH. EH is the sum of these n. Okay, EH.
Okay, you make an amplified choice at each layer.
Yes, and then you get to 1, 2, 3, 4, 5 by having more collisions. And then at this time, you make another choice, select some of the particles. You can choose, 4 and 5, okay? Or you can choose, 1 and 3, or you can choose, 1 and 5. It doesn't matter, it's a completely independent choice. And then you start with this choice and further expand. You have 1, 5, 6, 7, 8, you bring new particles, and then you make another choice at this time and so on. Okay? Okay. So this is a property of the molecules. And then let me tell you what is IM. This IM is a very simple thing. Next, the IM. Okay, maybe I shouldn't say it's a very simple thing. It's a conceptual very simple thing. So IM is a renormalized to epsilon to the minus. Okay, so basically it's n to the some power. This power is just for normalization purposes. It's a power that's related to the number of particles in M, but in practice it's not important. Important thing is this integral or probability of all collisions in M happen. And now this probability, we can write it as an integral. This is n to the some power times the integral. Okay, what is this integral? Okay, so first of all, you're having the variables you integrate. Basically, for each node, each atom, which represents a collision, which represents a collision, you're having one kind of variable, which is a time variable representing the time of the collision. So n is these atoms in the molecule and nodes, and this is the time variable. And for each edge, remember this is an edge, okay? This is an edge, and for example, this is also an edge. This blue one is also an edge. So each edge represents the particle kind of between two collisions, or kind of after the last collision or before the first collision. So in any case, in each of these edges, the particle travels linearly. It travels linearly. There is a velocity which is constant, and there is a position which goes linear, and you can always transport back to zero to uniquely define that position. Okay, so that means for each edge E, this is edge E, and this is a node N. For each edge E, there is a uniquely associated vector variable X, E, and V. It should be X, E, and V. So let's try it. ZE, so ZE equals VE. Okay, so basically you are integrated in all the possible time variables and all the possible vector variables. Of course, these vector variables are not independent. They are relations between them, and the relations are exactly because of these collisions. Then I'm having the product of n delta. This is a bunch of direct functions we'll see. And then finally, we're having this product of E F L D. So these are the initial data. So not initial data, but essentially they are solution of boson equation. Remember, we're having these functions F L tau that occur in the formula, and this will also occur in these integrals. So these are not explained, but in any case, this is a boundary function. And it plays no role, in the actual proof. Let me explain what this is delta n. So delta n is a direct functions that represents the collisions, the fact that we have collisions happening. Let's see if we put this is n, this is let's say E1, E2, E1 prime, E2 prime, or let's call E3, E4. It's just 3, 4. Okay, if we have any, atom n, and with 4 edges, E1, E2, E3, E4, the delta n is let's say it's a conceptually simple way to write it down, but each of terms is clear, has clear physical meaning. So this just means that the collision, remember that the x variable is the position transported back to 0, v is the velocity. So for example, this thing is really just equal to the position of the first particle at this collision, and this is the position of the first part, also the position of the first particle at the time of collision, because collision doesn't change the position of the particles, so you have this delta, and this must equal to this. And same thing, this is the position of particle, the second particle at the time of collision. This is also the position of the second particle at the time of collision, and these are equal. And this you see just elastic collision formula, the outgoing velocity of particle 1 minus incoming velocity of particle 1 equals this guy, the relative velocity dot omega, the projection, and this is the same. These are just velocity, just elastic collision formulas for velocities. And finally, this is a weight, you see, and this is the condition that the collisions happen. The distance of the two particles at the collision is exactly epsilon. Okay. So this is all formula, but really just word by word translation of the fact that the collision happens. Yes.
But so here, aren't you implicitly assuming that no collision occurred for particle 1 before time tn?
So this is you see, okay, so this is so basically we are, in principle, we are having this indicator function that no other collisions happen, but this will actually, in the practice, will come into you will have this product of something A not collide with B. Okay, so there are two ways we deal with it. Either we ignore it, we bound it above by 1. If we already have a good upper bound of this integral, we just bound these things by 1 if you want. Or we could just say that that this we can write as 1. So this indicator function of A not collide with B is like 1 minus indicator function of A collides with B, and if A collides with B, we just add it into the collision picture. We have add one more collision, and we get a different molecule. Basically, we think once we fix molecule, it's always understood that we are just only looking at these collisions.
Okay.
Okay. Yeah. Okay, we can talk more afterwards, but this is the formula, and then our goal is to prove the number of molecules and the upper bound of this ion. Okay, so we can continue. So let me write down the upper bound that we are trying to prove. So this thing, we'll use this picture later, but still erase it. So suppose in this the size of the molecule is equal to little m, and the number of recollisions. I think recollision corresponds to the cycle in the diagram. So basically, number of recollisions, just number of cycles, is rho. Then number of molecules m is less than absolute constant c to the m times log n to the c natural, and then the I of m, which is less than tau to the m times epsilon to the alpha times rho. Maybe not alpha, so that's probably beta. Okay, so here c is a constant, c is absolute constant, c is absolute constant, and beta is positive constant. Okay, so this is the thing that I want to prove. Obviously, if we have this, then everything is okay, because here C is absolute constant, and we choose out tau small enough such that tau to the m times C to the m is less than 1. So this thing converges if you sum over m. And if you sum over rho, obviously this is a log power. Remember, n is a power of epsilon, so log n is something like log epsilon. So this is power of log epsilon, but this is a polynomial of epsilon, which falls to the power of rho. So again, this absorbs this, and so everything is convergent. Okay. So this is our goal, and for the rest of this lecture, I'll try to briefly discuss this and focus on the second part. Oh, this first is easy, but before saying this, let me remember one thing, that is, where does these recreations come from? Yes. The size of the whole molecule, the single number of atoms.
The total number of atoms that you have.
Yes, which is comparable to the total of particles, which is comparable to the total number of collisions, in this under our assumption, this generic, this kind of typical case.
And the recursion is any cycle.
Any cycle. So yeah, number of think of like if you have this, there's one cycle. You have a this, you have another. If this, you have a three. Okay, just a number of cycles. Okay, so strictly speaking, it's number of independent cycles, because you're now not allowed to add two cycles to get a third cycle. But it's the dimension of the space of cycles, if you want. So okay, so we'll talk about the recreations. So there are two sources of recreations. The number of recreations. Rho 1 plus rho 2. So rho 1 is a number of recreations within a single layer. Okay, so remember, if you have a something like this, okay, that is this thing going on. So this cycle is a recreation, within a single layer. Okay, but you can also have those settings where each layer has no recreation. Each layer is a forest, has no cycles, but there are cycles, because you put together different layers. So this is cycles in a single layer. And then there are cycles, for example, if you have this, and this, okay. And when you build each layer, each individual layer, there is no cycle, but if you put two layers together, you're going to have a lot of cycles. Okay, so this is layer, cycles crossing different layers. And this is rho 1, and this rho 2. Cycle recreations, crossing different layers. So in our proof, we'll make one signification, that is rho 1 is equal to 0. Okay, the reason is that if rho 1 is small, we can pretend it's 0. If rho 1 is not small, then there is a lot of recreation kind of in a single layer. Then you can just focus on this layer, and you just, we know that the analysis of recreations is okay, it's doable if we have a short time, it's short time theory. And if you have a single layer, each single layer does correspond to a short time of length tau. So if there are many recreation within a single layer, this is a good case. We already know it. We know how to do it from the short time theory. That's why we're going to assume the rho 1 is 0, and we just focus on the rho 2, which will be simplifying a lot in our subsequent discussions. Okay, so with this, let us first prove this upper bound of the number of molecules. First, where is this? So the idea is that how to draw a molecule M. You first draw the molecule in each layer, and then you mash them together. Okay. Draw molecule in each layer, M, L. And now since we say that each layer, within each layer, there is no recollisions, we have assumed by simplification that this guy is 0. Then each layer ML, which is a forest. And it's well known that if we have a forest with unlabeled forest, then the number of choices of the forest given the number of atoms is exponential. So if ML equals little ml, then the number of choices c to the ml. And if we put these together, the sum of little ml is equal to little of m, and then we get product L C to the ml, which is c to the m. This is exponentially many in the size of the molecule. And then we draw each molecule, each single molecule, and then we still need to match them together. Basically, how do we match them? This is that if you have a draw molecule like this, we have a this molecule like this, and then there is a molecule like this. This is ML, this is ML minus 1. How are you going to join them together? What do is that you just okay, so it's essentially this. This is there. Okay, so then what you do here is that you select this edge here, select this edge here, and you try to match them, formally. Let me further again. So have okay, have this this is ML. This is ML minus 1, okay? And how do you join these two molecules to the same molecule? Do is that you join these two edges, you join these edges, and you put this into a big edge, okay? And you make these two molecules into one single molecule. And then you can see that by doing this, you have performed a number of these joining operations, and total number of joining operations is bounded by this number of by this whole number of equations, because basically if you have join these two and you create a new cycle, this creates a new cycle, or at most one new cycle. But and if you think the whole number of equations is rho, then you get this number of joining operations in rho, and the number of choices of these joinings less than log n to the 0. Remember, we have done this cutoff that ensures that total size of all the molecules is less than power. This is due to truncation. That the size of m is less than log n to c. And if it's bigger than log n to c, it's always a good case. You already have so many collisions, and you can basically do a trivial S. Okay. Any questions? So now we have this upper bound on the number of molecules, which is here. Now the main thing is to prove this upper bound on the I of m. Okay. So let me make one more simplification. That remember, this rho is the number of equations. we actually see that this rho is closely linked to this number of crossing particle lines. Remember, we're having this M, we're having this R of ML, which is a number of crossings, at each level, each layer. So this we already have. Erase it. Nodes. And rho is less than max in L, SL, or SL is a set of these particles crossing a layer of L. Remember, we have this picture. This red particle, we draw them, sorry, the blue particles first. The blue particle, we draw them as the particles crossing this layer. This is L tau, L minus 1, and so on, and they are kind of connecting to other things, and in the end, you are seeing this number of red particles that cross down, and you have green particles cross down, and so on. So this R of ML is a set of these crossing particles or crossing edges, you can think, and this SL is the size of it. And then the thing is that this number recollision rho is less than the maximum size of SL. And this is also easy. Basically, remember this joining process we just discussed. If we only have individual layers, a molecule in each individual layer, then there is no recollisions. But if we join one pair of edges, we create at most one new cycle, and then the total number of cycles just bounded by the total number of joinings we get, which is the sum of this SL. But then L is 1 to big L we treat it as a constant, so this is just comparable to the maximum of this L. Okay, so I have to make a number of simplifications. So the real proof is slightly more complicated, but following this same idea. Okay, and now using this fact, we can just replace rho by maximum of this SL. So this epsilon to the beta maximum SL, because this is a quantity that we really actually see in our proof. So this maximum. Okay, so now we can start talking about this how to enter this IM. So the key kind of key operation in the estimating this IM. Remember, IM is a big integral. We already wrote down there this integral of many variables involving many derived functions. Okay, so it's a big integral involving the big molecule. Now M is multi-layer molecule. You can have here and branchings and cycles and all kinds of structures there. M is a huge molecule. So how to estimate this huge integral associated with this huge molecule? The thing is that we're going to do integral, in steps. Okay, so first step, we first integrate in these variables, and second, we integrate in the next set of variables, and we integrate in the next set of variables, and so on. Okay, so I'm going to fix a certain order of integration, what we do, and this order is given by the so-called cutting operation. Next, we discuss the cutting operation. So how do you do the cutting? So let's say we have arbitrary molecules. Let's say we draw a molecule like this. So let's say we draw, so let's say, okay, so they have this M, so I have this, the 2 atoms here and 2 atoms down. Okay, and there are associated edges, okay. So now what we do is that we're going to do a cutting along this line, let's say, and then we call this molecule, this atom, N1, this N2, N3, N4. What we do is that we're going to first fix the variables associated with the upper half. So we fix these variables, okay? And then we're going to integrate in the variable associated with the lower half, integrate in this time variable, this time, and this vector. Okay? So let's give it some name. So there is this Tn1, which is time variable. This Tn2 time variable, and there's a Tn3 time variable, and there is Tn4. Okay. Remember, we also have these these vector variables. And then there is this EJ, E1, E2, E3, E4, E5, E6, okay? And now this edge, remember, is a common edge connecting the upper and below. So this is called E7 and E8, E9, E10, E11, E12, E3, okay? So you see the whole integral I of m is the integral of all those variables, all the T and T1 is called T, okay, so Tn1, Tn2, Tn3, Tn4, and the vector variables Z, E1, E2, E3, all the way to E13. Okay, and then what we do is that we first fix those variables, we integrate in the variables below, and then we and then after this we integrate in the top variables. That is m is the integral of something dt1, let's just write dt1 is dtn1, dt4, dz1, dz13, okay, write it as, so we first integrate in the variables below, so we have dt3, dt4, and then we have dt8, dz8, dz13. And then we integrate back in dt1, dt2, dz1, dz7. Okay, remember we are first fixing these variables e1, e2, and fixing up to e7. Okay, and we integrate in the rest variable e8 and w13, and then we first fix these, integrate these, and then we finally integrate back. Okay, so what is the advantage of this? What I did here is that when we integrate in these remaining variables, we're only dealing whatever molecule that is in the lower half. We don't care about upper half because there is no variable in the upper half that occurs in this inner integral. On the other hand, when we integrate in the outer integral, we only have variables in the upper half, and we don't have any variable in the lower half. So this outer integral again has nothing to do with whatever happens in the lower half. Okay, so as for this single edge that connects the upper half and lower half, okay, so we are integrating it together with the upper half variable. That means when we integrate in the lower half molecule, this value, this Z7 variable, is viewed as fixed. Okay, and after this, when we integrate in the upper half molecule, we're still integrating them. We're integrating as a free variable. So is everything clear? So in this way, we get to this critical notion of cutting. So let me draw you an example. So by doing a cutting, we turn this into, two molecules. The first one is this. If you want, you can sign it still the same. E1, E2, E3, E4, E5, E6, E7. There is this T1, T2. Okay, plus these things. Okay, we'll call this E8, E9, E10, E11, E12, E13, except that we put a red cross here, indicating that this edge is fixed. Remember, when we do the integrate, we'll do this proving theory. We first fix the value of Z7 corresponding to this edge. And then so when we integrate in the integral, this variable is fixed. So we're not integrating in it, it has been fixed. And then we integrate in only backwards, in this edge. Okay, so let me draw this edge as a yellow. Yellow is corresponding to this edge as broken, in the frequencies. Okay, so this is the cutting. It corresponds to application of full beam. Of course, we need to apply it in a very clever and creative way because this we have to design our cutting algorithm, which comes later. But in any case, we have this. So when we do the cutting, we cut one submolecule. This is cut as free. and this we cut as fixed. So this notion of free and fixed really corresponding to in what order you're iterating these variables, or iterating this, you're first iterating, this first fixing this in this submolecule, and you treat it as fixed, and then you iterate back here in the free variable, so you treat it as free. So basically, if you cut something as free, something as fixed, what you do is that you break any edge connecting an atom in the free set and the atom in the fixed set, and you turn this into a free edge here in the free set, and the fixed edge with the red cross in the fixed set. Okay. And this way allows us to break this integral I of m of the big molecule to the integral of I of m1 and I of m2 of two smaller molecules. And the key, you can see from here, like this thing you can factorize, basically you can factorize this product, you can factorize, remember this is a product of n, right? So you can have think of product m belongs to m2, and you have a product m belongs to m1. So this thing can factorize, and then it's effectively you get this result that I of m less than I of m1 times I of m2. And this way, if you keep doing cutting, you're going to break your big molecule into large number of small molecules, and then you can bound your integral by the product of these small molecules. Okay, this is a key thing about cutting. And now let me show you the examples of the small molecules we'll get in the end of the cutting process. So there will be a number of them. So we're done with this part. We need to prove this. So then the result of this cutting is what we would call the elementary molecules. That these forms. Having a two fixed edge. So this is called the degree 2 molecule, because the fixed edge doesn't count as a degree. There is one fixed edge. This is degree 3. There is this no fixed edge. This is degree 4. And there is this 2 atom thing with exactly 2 fixed edge. So this called 3, 3. So degree 3 connected to another degree 3. Okay, so I'll roughly explain what this means. This means that if you have a collision and these two edges being fixed, means that the incoming velocities and the positions have been fixed in this collision, and you have outgoing, which is also completely fixed, and you're just integrating the delta function, which give you some just an indicator, just 1. And then this is something different. Only one of the incoming velocity is fixed, and the other is free, so you can still integrate it, and you get a real integral, which usually also give you a factor of 1. And this thing we'll see is a bad thing, because you have one free thing that is kind of wasted. You don't have any restrictions. So this is what you call bad. And this is what you call good, because this precisely corresponds to the scenario where we can get the extra power of epsilon with the recollision that we discussed yesterday. That let's say you can also think that you have this fixed sorry, not this fixed edge. I mean, let's say this fixed edge. Okay. Then you are having this is fixed, and you have free variable, you integrate it. So the condition is that this has to collide with this, fine. But afterwards, it again has to collide with another one, and you have this extra collision restriction. Again, as I said, collision restriction basically restricts you to a tube. Okay, but you have a 2 tubes there, then most likely they're going to intersect as a set of much smaller volume, and then you should get an extra factor of positive power of epsilon from this integral. Okay, so these are the elementary molecules, and then our goal, as if we still have 40 minutes, our goal is to show that there exists a cutting sequence. Remember, this cutting sequencing a priori is completely arbitrary. You start with a huge molecule, you can do this cutting whatever you want. You can choose any sets, you cut it as free, you cut a complement as fixed, okay? And after that, you can keep cutting each of the sets again in arbitrary way. So there is a complete freedom you can choose. But then in the end, you need to choose a suitable cutting sequence, cutting algorithm that cuts your big molecule into these elementary molecules, and you need to make sure the number of good overwhelms the number of bad. Let me just say this. So choose a cutting sequence that cuts n into elementary molecules with this number of three threes, number of good objects minus, let's make it this one. So number of good objects is bigger than a large constant, let's say 100 times of bad, and the number of good is also enough, bigger than maximum L of epsilon. Remember, each good molecule gets you a positive power of epsilon, but epsilon to 0 plus, this epsilon to minus d minus 1. Okay, so you need this number of good to be overwhelmed the number of bad, and number of good also has to be bigger than the kind of this power you want to have on the right hand side. Okay, so now remember we have started from this formula we proved yesterday, and we define this notion of IM, which is this huge integral involving all these edges and all these vectors, velocity for these edges, and these nodes for these atoms, and all these direct functions involving corresponding to these collisions. And how to deal with the integral we estimate by the cutting, and the cutting tells you the integral is less than the integrals of the smaller molecules. So then you just need to cut this into smaller molecules, which are elementary molecules, and by elementary calculations for each of these, we can calculate the value of this IM. This is O1, this is O1, this is negative power of epsilon, and this is positive power of epsilon. Okay, and then you need to. The goal is to find a kind of sequence that satisfies these two problems. So see, we have turned this analysis problem into a pure combinatorial problem of studying this graph and cuttings. Okay, so let me keep going on. So in order to construct this kind of sequence, so there are a few few steps. So the first step is that remember this molecule has many different layers. It's ML, ML minus 1 all the way to M1. This big L, the number of layers. So this big L is a constant, but it's a large constant. You can think it's a 100 or 1000. Like it doesn't go to infinity, but it's a large constant, and not just 2 or 3. Okay, so our first thing is to show that we can basically reduce the multi-layer case to the 2-layer case. So in some sense, we're already seeing the 99% of the not 99, but like 80% of the difficulties already when we have 2 different layers. We will see like why already with 2 different layers we're having a lot of trouble. The reason is the following. Let's erase for now. Because the problem again comes with recollisions. If you have only 1 layer, since we're assuming each layer has no recollisions, then this verse just have no recollisions, have a false. Okay, let's see. You have 2 layers. Is that you could have things like this. You can keep going on. Then you may have Well, this is just one example of the what you may see. Okay, keep going on. Let's see. What happens is that if you view the graph in each individual layer, it has no cycles. It's a forest. Actually, here it's a tree. If you view it within each single layer, the top layer is a forest. The bottom layer is also a forest. Okay, but if you put two layers together, you suddenly see there are lots of cycles, and the number of recreations can grow to extremely huge. Okay, so you need to find a way to analyze all these pictures, especially those cycles that form because you join two different layers. And these we already seen them like in the two-layer model and not necessarily in the multi-layer. Okay, so because they were thinking on the two-layer model, the multi-layer model in reality is not that much more than what you would see in a two-layer model. Fortunately, there is something called a layer selection algorithm, which allows us to effectively reduce the case of multi-layers, like 100, 1000 layers, as long as there is a finite number of layers, to the case of two layers. This is the cutting sequence. So this is the algorithm. We talk about the first ingredient, which is this first ingredient. Is a layer selection. To see how this works, again, we need to go back to this set of R of ML, and these R of ML sets. Set R of ML of particles crossing into layer ML. Again, let's just look at this picture. So if you have this crossings. Okay, this is the ML set of R of M. I'll show you how this layer selection works. Okay, so let's say, so first this R of ML, we have many crossings. So in fact, we can choose a suitable this layer L such that these particles, they are connected to the top and connected like in the picture above. So this is the top layer, this layer, big L sum. Okay, so they have to be connected. Somehow they have to be connected. I'll not explain why, but essentially this is because that eventually each of these particles is going to collide with one of the root particles, one of these H root particles. The root particle, the initial root particle, the root particle we see at this initial accumulation we have is this, and this number is typically very small. H is typically smaller than the maximum L. So we know that these green lines, these blue lines, they are connected above. Remember, our goal is to find sufficiently many, cycles or recollisions. We need to locate sufficiently many recollisions in two layers only. Remember, we're doing layer selection. We're trying to reduce a multi-layer case to a two-layer case. Okay, so we have these green lines, so blue lines that all connected together upwards, upstairs. The question is whether they are also connected downstairs. If they are also connected downstairs, then okay, if you have one connection downstairs, they also connected upstairs, you get a cycle already, which represents the recollision. Like you go here, here, and you go connect here and diverge here, you get a cycle. Now, if there are many pairs of things that are connected, you get a cycle. You get many recollisions. So this happens, for example, when these blue lines are connected to each other within this layer. Okay, then you get cycles. If there are many such things, you get many cycles. If this is the case, then we're already done because we can ignore whatever happens below layer L because we already see these many cycles in this layer ML alone and not going down to any layer below. We can ignore everything here. Okay, so now let's say they are not connected. They're not connected together. Remember, what is our property, our corollary of this property of M? So any of the blue is either connected to the blue in this layer, or they are connected to another blue eventually in some lower layers. Okay, so let's say they are blue, they are not connected, they are connected like this. Okay, and then we just go to the next layer. This is ML minus 1. And let us ask, are these blues, are they now connected to each other in this layer and ML minus 1? Are they connected? If they are connected, okay. Connected, then let's say they're connected here. Good. Then we just look at this layer. Basically, we just combine, this ML, with this thing. Think of this as one layer, and think of this ML minus 1 as a second layer. The thing is that since these blue edges, they are not doing much in this layer, in particular, they are not connected to each other, you can show that even if you add this layer into the picture, the upper half still remains a tree, and the connection happens only on the lower half, which is this NL match. Okay, so this is the picture. Okay, and now if these blue lines again are not connected in this layer, you just go to the next layer and so on until you get the first layer where these blue things are connected. Think of this picture. Think of this. Okay, so there is this blue things, and they are all connected together, kind of upstairs. Let me just draw this picture. It's not necessarily the simplest picture, but let's draw that. That just showing the idea they're all connected together. Okay, and then this layer, they are not connected. Fine, go down. And next layer, again, they're not connected. We keep going down. Okay, so if you want, and okay, and this layer, and suddenly at this layer, they get connected. They get connected means that here there are many such connections. Okay. Then what you see is that if you combine these things, everything before this, so this is the lower layer, like the down layer, layer LD, and if you combine everything straight above this critical layer here, then everything above is still a forest, even if you put different layers together, because each layer itself is forest, and these edges are not connected. If they're connected, you get cycles, but they are not connected all the way down here. So if you put everything together, it's still a forest. There's still no cycles. And then suddenly, when we go down here, suddenly have a lot of cycles, and okay, you see whatever happens is in this cell we call this M upper, and this cell we call this M down. Okay, then everything above, okay, we can forget about it. Everything below, we can forget about it. And then we only focus on this cell, and this whole thing is a forest. You can think of, mentally think it as one layer, and then we can think of it as an equivalent to this picture of you have a forest here, you have a no cycle picture here, okay, so whatever you have, and then you have a no cycle picture there, okay, but then putting together, you suddenly see a lot of cycles or kind of collisions, and that only happens in these two generalized layers. This is a layer selection. Basically allows us to, okay, so if you have a L, L layers, and of course, this L cannot be very large. It's a large actual constant. Not actual constant, it can grow very slowly like log, and this is the main kind of reason why we need this log kind of upper bound. Anyway, this is the thing of as constant, and then you can have this multi-layer thing that has sufficient many recursions. Then you can single out two layers, this and this, such that each layer is still a forest, and there are still a lot of recursion between these two layers that happens when we put these two forests together. And this way, we effectively reduce. Remember, our goal is to construct cutting sequence, cutting algorithm for this particular big molecule. We can effectively reduce to the case of smaller molecules which contains only two layers. Yes.
Excuse me, maybe there is something I'm missing. In the picture that you're drawing,
Yes.
you give the feeling that all the reconnections
Yes.
happen at the same level depth, right?
Yes.
But they could happen at very different depths.
Okay, so you ask this, going from this to this, so you see, you have a goal here, you have a goal which is rho, let's call it rho, okay? So just come, okay, so you ask, going from this layer to this layer, how many reconnections you have, how does it compare to rho? Is this less than much less than rho? If it's much less than rho, you go to next layer. If it's already bigger than constant rho, you just stop there and you're good. Okay, so let's ask this. So let's say you have 100 layers.
Yeah, but okay. Is it clear that you'll be able to have some kind of cutoff that?
Let me tell you.
Okay.
So let's say going from layer 100 to layer 99, let's say you have a row, 100 reconnections. The question is row 100 bigger than 100 to the minus 100 times row?
Okay.
Yes, we stop. We already have a constant times row and we are good. No. Then ask, is row 99 bigger than 100 to the minus 99 times row? Yes, then we stop. Because this is bigger than constant times row, and it's also bigger than 100 times row 100. So this row 100, which is error term, will not matter in our argument.
Okay.
Okay, so if no, then we further ask,
Okay.
is row 98 bigger than 100 to the minus 98 times row? If yes, then we stop. And okay, you cannot keep saying no, because in the end, row 0, row 1 will be everything.
Okay.
Okay, and then we get this critical, layer that we construct.
Okay. Thank you for
Okay.
the clarification. Thank you.
Okay, so this is, now we are reduced to the 2-layer case, and this is the second ingredient in the proof that we'll be doing the 2-layer case. The second so assume with the following assumptions. Now M contains 2 layers, one up and one down, and MU is a forest, or let's assume it's a tree, just for simplicity. Tree. And from these reconnections, there are a lot of connections between MU and MD. So the number of edges between MU is equal to rho. And the goal is still we find a cutting sequence such that the number of 3 threes is bigger than 100D, 100 times number of degree 4, and the number of 3 threes bigger than 4. Okay. So in order to do this, let me consider a number of simplified models. So there is this hold on. So going from the multi-layer case to 2-layer case is already a big simplification. But here we will make even more simplifications. Basically, what happens is that you consider there is a upper bound. So this upper is MU, lower is MD. Okay, we are going to consider those atoms, those nodes in MU that can connect to something MD. Okay, so if something. Okay, so this is a you can think of it as a crossing or kind of UD connection. So consider the number of edges of this, and then consider this atom, let's call it N, whether it has one such connections or it has 2 such connections. Okay, so define this 2 connection atoms in N that connects to two atoms N in Mu, two atoms in ND. Okay, well, you think of it as, if these are two particles, think of it as, these two particles, they collide and they have recollision kind of back. They have a number of collisions in MD, but they have recollision in MU. Okay, so this is the two connections. And then, of course, you have one connection, which is this. And this only have one. Okay, so the first question we ask, first case we consider is, let's say there are many two connections. This is a relatively easy case. Okay, so there are relatively easy case. So this can I'll show you how do we get a 3-3. How do we get a 3-3? Okay, now I'll not show you how to avoid the degree 4. There is an algorithm designed for that. I'll show you the basic idea how to get a 3-3. How does this 3-3 occur? The thing is following. Remember, if you cut this thing as free, basically, if you cut something x as a free, you cut y as a fixed, and then you are going to get this is basically cutting algorithm will tell you that you get a free edge at x and a cross fixed edge at y. Okay, so remember, if you cut this guy as free and also cut this guy as free, then these things will have two fixed edges there, because this connected this, and if you have this two fixed edge, this will be something we call degree 2. Remember, this is one of the elementary molecules. It's a 2 molecule. It's degree 2 because there are two fixed edges. The fixed edges do not count in the integration. So let's call this M1. M2. Okay, so basically what we do in this case, here we cut atoms in MD in the suitable order. There is some order we need to choose, but this is not extremely important. The thing is that basically each atom will have degree 3 in a cut. So why degree 3? Of course, the first atom you cut will have degree 4. But then once you cut one atom, subsequently you cut the atom that's connected to it, because M2 is connected. So these are connected eventually. Okay, so let's say you cut M1 first. And when you cut M1, this connected atom, you're going to get you're going to get a fixed edge here. So this guy will be degree 3. And if you cut this, you're going to get a fixed edge there. The subsequent things may all be degree 3. Think of this way. Since M2 is MD is connected, so this is not a real thing, but just an example showing you how to do. You cut this, you cut this, just formally you cut this way, and you get a fixed edge here. So this is degree 4, but this now has degree 3, and you cut this, again, you get a fixed edge here. And then this has fixed edge here, and this has fixed edge, and this, and then this. Okay, so see that each time you cut, each thing, subsequent thing you cut, except the first one, will have degree 3. Now, let's say you cut M1 before M2, then when you cut M2, M2 will be degree 3, which means that M2 has degree 3. It's cut, but in the meantime, N also has degree 3. Because M1 has been cut, if we cut, then we get a fixed cross, at this end. So it has still it has degree 3. Which means that when you have any two connections, the time when it's cut is always a 3-3, because at this time this N2 is connected with N, and N2 has degree 3, and n into 3, so you get this 3 kind of for each such two connections. Okay, so this is one of the kind of the basic kind of mechanisms where we can get to these 3 molecules. Let me just for definition of 3 this means that you have is a 1 cross here and you have exactly 1 cross, so 3. Make sure you have exactly 1 cross here and exactly 1 cross. Okay. So this is a case when there are the relatively easy case when there are many kind of 2 connections. Okay, then you get enough 3 is very simple. Now let's say there are not many 2 connections. So in fact, we'll assume there is no 2 connections. If there exists some 2 connections, we'll just remove them. The number is negligible, so you are fine. So let's say there is a no 2 connection, which is the kind of the main case. No 2 connections, that means that each atom in the top in Mu has at most 1 edge connecting to the bottom. And let's say we consider those atoms that has 1 edge, 1 or 0, those has 1 edge connecting to the bottom. Let's call it a set X. It's a subset of upper limit. One edge with NP. Okay, so let me show you 2 examples. Like in 2 examples, we're going to do different strategies. So, which leads to dichotomy what we're considering. For example 1, well, X is a whole, let's say example 1 is this. Let's say example 1. So this is MU, this MB, and then we have basically how do I draw it? So MU is something like this. And this is a kind of zigzag thing, and then this guy, each of the bottom thing is the 2 connections. Like this, and then this, and then this other thing I just like so this is next and there are some okay. You see in this case the 2 connections are one thing that there's no 2 connections. Yeah, so there's still this. Okay. There's this one no 2 connections, and then you have this, and then you have this, and then sometimes think of this as arbitrary long chains. There are many kind of such 1 connections. In this case, what is set X? Set X is this atom, this atom, this atom, and this atom. You see that this X is separated. The atoms in X are separated by atoms that are not in X. So these red yellows are in X. These other things are not in X. So this is an example. The other example, let's say example 2. Well, X is everything above. Let's say you just have this, this, this. Okay, and everything here is X. Of course, the size of X is the same in both cases. But the difference here in example 1, the X are separated by others, and example 2, X is connected. Okay, and so this case, we'll see example 1, we'll do something pretty relatively simple. What we do is that we cut everything MB. So this MB, this MU, this MU, this MB. Okay, in example 1, we just cut everything MB. Okay, just do a manual experiment. If you cut everything empty, then for each of the yellow ones in MU, you're going to get one cross. Remember, we cross. We have one cross down here, one cross. Okay, then each of the yellow things will have degree 3, and everything else will have degree 4. It turns out in this case, can exploit the fact that these degree 3s are separated by degree 4s to get as many 3s as we want, but this is not possible in example. So we still have 5 minutes. Let me show you what we do with example 1 and 2, and then we get to dichotomy. We have this. So if we cut, imagine if we cut, we're going to get only these things. Okay, so there is a fixed end here. This fixed. Okay, so now you see, let's say there is also a fixed end here. Okay, so apparently you think this guy has degree 3, this guy has degree 4, degree 3, degree 4, degree 3, 4, 3, 4. You can abbreviate it as this. Now see, the key thing is that the degree 3 atoms are separated by degree 4. So let's say if we cut this degree 3, okay, if we cut this degree 3, then we break this edge and we get a cross here, return this degree 4 into degree 3, fine. Then, now this guy becomes 3. Now you already see a 3, 3 here. So this, remember, this is the kind of the precise, good structure, the only good structure we're hunting for, and now we're getting 3, 3. Now we just cut it off. Okay, so we get one good thing, and now we affect one edge here. This guy again becomes degree 3. Now so next is also degree 3 again. You get another 3, 3, and remove it, and this guy becomes degree 3. Again, this becomes degree 3, and you see you just keep getting these good objects. I mean, if you want to do this picture here, saying you first cut this. And we get a cross here. But then this is 3, degree 3, degree 3. So cut these two together. You get a cross here. It's 3, 3. And this. And then finally you get this last one. So you see, this guarantees a good scenario. We'll keep getting these good molecules. And in example 1, where these things are separated by the rest. Now, what if you have to do this for example 2? Then you see a precisely in bad scenario, because if you do this, just to make experiment, imagine you cut everything there, then you break every of these edges here, you get a cross. Everywhere here. Now everything here becomes degree 3. So schematically, you're having these 3, 3, 3, 3, 3, 3. Okay, and then you can get 1 degree 3, 3. You can get one good thing. Okay, so because you move it, but then this will become degree 2. And degree 2 is not a good thing. You cannot gain from degree 2s, and you need to remove it, and this becomes degree 2. And remove it, and this becomes degree 2. And you only get 1 3, 3, and everything else is completely degree 2. I mean, you can just look at this picture. You can cut this, fine. But then this is degree 2. Okay, and then you cut this without any gain. You cannot gain anything from degree 2. And this again degree 2, and you keep cutting, and in the end you don't gain anything beyond the first first good small. So basically, this is example 1. You gain as many as the number of these yellow atoms. But example 2, no matter how many yellow atoms you have, you only gain once. So this is. So this tells us example 1 is good. Example 1, we just do what we just described is not sufficient. Now in example 2, this is not, and how how do we decide this dichotomy? Is precisely think of the number of the yellow atom. So the yellow atom forms a set called X. It's precise by counting the number of kinetic components of X instead of the size of X. So then from these 2 examples, we get to this dichotomy. Number of kinetic components of X is bigger than rho or less than rho. If it's bigger than rho, we're in example 1, and we are good already by the argument just before. Example 1. Good. Example 2. And precisely what we do in this case, we'll do something different. If we have last 5 minutes, I'll explain this last thing what we do for example 2, because that covers everything. Remember, if there are many 2 connections, with the easy case. If there are few 2 connections, we imagine there is no 2 connection. If there is some complication, but that's kind of not important. Then we ask this whether the number of components of X is bigger than rho or less than rho. If it's bigger than rho, we do as example 1, we are good. If it's less than rho, this kind of last case. So algorithm. So what I will present here, since I don't have much time, is a much simplified version, but the real version is slightly different, but following the same ideas. The idea is that each time cut a lowest atom in X, and then if we see a 2-degree streets adjacent in the lower layer ND, we cut it. And for technical reasons, we also need to remove the following sentence. See this. We'll cut it. You can ignore the second part. I mean, so just purely for technical reasons. But basic thing, if you see anything, any of the structure hunting ND, you remove it. So just keep hunting this in ND, and this is a kind of a greedy algorithm or whatever you may call it. And then if not, go back to X. Well, I only said X. I didn't say that outside of X you do something slightly different called the ARC algorithm, but I'm not talking about that. We imagine X is the whole thing. Okay, and you go back to X and you keep doing. So let me just show you how this works. Okay, so if you have example 2, your X is the whole thing. Okay, so let's see. We start with the lowest in X, so everything here is X. So let's say we cut this. Okay, we cut this, that means we cut this. Get a cross. Yeah, and cross that. Okay, so now if you look at this ND, this is ND, there's 1 degree 3. You don't yet see this structure or this structure. Okay, so do you keep the next lowest atom in X, which is now this atom. And this. Okay, I'll get cross here and cross. Now you see there is this 3 ND. So you cut these together, you get a 3, 3. This is a good thing. And now there's a special case. Remember that this is a degree 3. This is also degree 3. So it's a 3, 3 component, 3, 3 atom crossing the MU and FD. With one thing MU, one thing FD. And you should also cut that. So I didn't say in the algorithm, but if you see any 3, 3, you cut it. Get this. Okay, this is a good thing. And then again, you see this is this connected with this, and then you keep cutting this. Yes. Get this. Keep going. Each time you get a good object, and finally we get as many good objects as the length of this chain. So let me make one final remark that by doing this, actually, we get a number of degrees. The good components is bigger than equal to rho. Essentially, it's because of greedy algorithm. Whenever we see anything in MD at all, we remove it. So this is like we keep hunting for it, and eventually everything will be kind of hunted, will be obtained in this way. I mean, the bad thing is that by doing some naive argument in the upper layer in MU, we may get this degree false, but only at lowest atoms in X. And here this final ingredient, like we only get lowest atom in X, so we need to count the number of lowest atoms in X. Now the nice thing is that since everything in X is going to have an edge connected to the bottom, let me draw it here. We have an X, okay, so this atom, lowest atom in X, so it has the one child, this MD, U, okay. So you're going to have, 2 parents, okay, and then see these 2 things. Each of these is in X, so it has one child in MD, but then it has another child which is this atom, so you can only have parents there because you can only have 2 parents and 2 children. And these guys again, they're going to have one thing going down, one thing going down, one thing going down. So they cannot have any other children. You have to keep going up, which means that each kinetic component of X, has only one lowest atom, which is this thing here. Which is this thing. Each component X has only one lowest atom. This means that the number of lowest atoms in X less than number of components of X. And precisely by this dichotomy, we're assuming this number is negligible compared to rho. And then we're good because the gain is much bigger than the loss, and then we're. So this completes the whole proof. Let me just summarize a little bit this last piece. Basically, we start with 2 connections. If there are many, we are good. And then in the case of no 2 connections, we define this set X, and we consider this dichotomy defined by the number of components of X. If there are many components of X, we first cut this MD, and in the MU, we have these degree 3s in X, which are separated by degree 4s, and we can get a sufficient number of gain. And on the other hand, if the number of components of X is tiny, then we do this algorithm, which is really in chronologically is the first algorithm that we found, but okay, in the logical order, like we will be treating it in the last. But in any case, we keep doing this. The gains have a rho only to control the loss. The loss is precisely controlled by our assumption on this dichotomy, using the fact that each component X has only one lowest. Okay, so this way we show that for any 2-layer molecule, you can construct a sequence that satisfies our need, and then by doing this layer selection, we can extend it to general arbitrarily finitely many layer molecules. And then by this cutting lemma, this estimate, we can get the control of these L1 norms of these objects. And by adding this together, we get this bound times this number of choices times upper bound, which gets the fact that this guy is less than epsilon 0 plus in the limit for any finite time. And since this guy is found very interesting L1, this dimension L1, which means that this thing gets approximately factorizing L1 after every time that we have when the solution exists. So this then this.
Thank you very much. Thank you. Are there questions? No, maybe, yeah. So Professor Lavermont has a question, so you can please.
Yeah, hi, that was very nice. I have a question about dimension. You had said two questions about dimension. So you'd said in your introductory lecture that so far you can only treat dimensions 2 and 3. Did I remember that correctly?
Dimension 2 and 3 in the torus case.
In the torus case, okay. And so I would think higher dimensions should be easier because there's more room for things to get decorrelated. So what's the, so my first question has to do with why is that restriction to 2 and 3?
Okay.
I could ask the second question too. I'm confused by dimension 2 in the sense that there's so much correlation that happens in dimension 2 that physicists observe first numerically the long time tail phenomena and realize that the naive scaling to get to a macroscopic or even a mesoscopic description has to be fundamentally different in dimension 2 than in dimensions 3 and higher, at least formally. And yet I don't see this coming in. So it's really where does the dimension coming in? Because a lot of what you did here seemed almost dimension independent.
Okay, so yes, indeed, most of the things are dimension independent. So okay, so the part that depends on dimension comes from the estimate of these elementary molecules. So remember, we have basically these three things. The estimates of this, so I have a cross here, a cross there. The estimates of this depends on dimension. So what happens is that it has to do with how many exact powers you gain. I mean, in the main algorithm, it actually doesn't matter. But there is this error term, like I didn't really mention about error term with many recursions, bigger than 100 to 100 recursions. And there, basically, by assuming there is such a cluster with so many recursions, we need to gain a fixed power, epsilon to the d minus 1, which is 1 over n, of course. We lose the extra factor of n, we need to gain this back, and we need to gain this power. And it has to do with that in different dimensions, when you have these three string molecules, the gain is not exactly the same. So basically, so there is a case, like when you have a three-string molecule, the time, if you have T1, T2, if you have a T1 minus T2 is 01, which is something you can achieve, say, on a torus, then this, I of m is less than epsilon to the, I think it's minimal of d minus 1 and 2, which is d minus 1 in 2D and 3D, but in higher dimension, you can only get epsilon 2 instead of epsilon d minus 1. Remember, you need to gain epsilon d minus 1, which means that in high dimensions, you need to do more kind of a combinatorial thing to estimate kind of more complicated molecules instead of just this one. I mean, we do believe by estimating the more complicated dynamics, we can indeed get these to high dimensions, but this will get things more complicated. So we decide not to do this in our work. On the other hand, in the RD case, you don't need to do this, because there is a BFK theorem that you can have this outer bound number of collisions, and then you can kind of get away with it without it, and then you don't need to worry about dimension. So it really has to do with the precise powers in the estimates of these good molecules.
Okay, so that explains why you didn't get why you have not yet done dimensions 4 and higher, but you're optimistic you could do that, I guess.
Yes, but then we'll need to do more complicated integral calculations.
But how about the dimension 2 question? Because that's an established in the sense of physics result that you should get divergences in the correlations. It's called the long time tail problem in physics. This was observed in the late 50s when they were first doing molecular dynamics simulations, and since has a lot of theoretical support. However, now that said, there's always the issue of mathematical rigor, but it seems pretty well established in that community. And I'm just wondering if you've thought about that, or it could be you're just the hard sphere problem makes it special.
Well, at least in our calculation, which concerns the hard sphere problem, we don't see any. Let me see. Is there any special problem about dimension 2?
I mean, basically, things come back and hit each other all the time. And in dimension 1, it's all the time. In dimension 2, it's frequent. And that's the problem, is you get correlations building up very quickly in dimension 2, whereas in higher dimensions, there's enough space that things don't see each other again for a long time, if at all.
But if you're in Boltzmann grad, then the average number of collisions or fixed particle is still a constant, isn't it? Right, because CON equals epsilon minus d minus 1, so the expected number of collisions of a fixed particle in the fixed amount of time is still a constant, no matter what dimension it is. Of course, Boltzmann grad doesn't make sense in one dimension. But
the Boltzmann grad argument is sort of presuming independence. It's using the old Clausius mean free path argument, and it's just observing what has to be in that argument self-consistent to see a kinetic equation come out. So it doesn't really answer the question. The hope is rigorous analysis should see this difference in dimension 2 from the higher dimensions. But I'm just curious about it. I don't see. I'm trying to put two threads together, and it's just something to think about.
So in our calculations, maybe things are different if you have different models, but at least in the hard sphere, I don't see anything special about dimension.
Okay, that's a fair answer. It can be thought about more.
Thank you. Other questions? Maybe I have a naive one. So as you said, you use a combination of combinatorial arguments and some estimates of integrals. Instead of the combinatorial arguments, do you think it would be possible to, say, use results on the structure of large random trees, saying, okay, this type of structure happens with such frequency statistically, and such other structures happen with another frequency. Of course, it's similar to a combinatorial argument, maybe not entirely, right? You don't actually have to do the counting by hand, and you have some abstract results doing the job for you. It's very vague, but do you see what I mean? Or
yeah, so basically you say instead of estimating this IM kind of uniformly, we try to say that with high probability, our M should look like this, and we have good estimates. Yeah, that may be possible that if we can identify some simple structure of M and say with high probability and low probability thing we estimate trivially, maybe it's possible. I mean, we haven't thought about it.
okay. If there are no other questions, then let us thank the speaker again.